We're going to be reacting on the world most challenging project. Let's get down to the video. Thank you very much for watching.
This is the world's most challenging construction project. The largest and most powerful nuclear fusion reactor ever built. An amazing team of scientists and construction workers are trying to replicate what happens inside the sun, potentially unlocking a source of clean and virtually inexhaustible energy. And it's demanding one of the biggest international collaborations in history.
The answer has eluded scientists for decades.
Now, it's being seen as the great hope for generating clean power.
But if it does work, it could help save the planet.
Today is an historical moment.
Successful nuclear fusion has long been a dream for scientists worldwide.
No fewer than 35 nations are teaming up and combining their strength to build something that's never been built before.
Without that extraordinary partnership, the epic International Thermonuclear Experimental Reactor simply wouldn't be possible. Although its origins can be traced back to the mid-20th century, a lot's happened here since I first visited in 2022. Back then, we only scratched the surface of what's really going on inside these walls.
We are building arguably the most complex machine ever designed.
I just cannot believe the scale of the engineering challenge.
To build a device that is this complex is a pharaonic or Herculean sort of project.
It's such a humbling experience. I got goosebumps just talking about it.
Building something together with people from all around the world, it's one of the greatest things you can dream to work on.
I'm here to see how this amazing team of people is managing this planet's most monumental build. I'm driving through the south of France and I've got a very big smile on my face, not just because the sun's shining, but because I'm on my way to see the world's coolest construction site.
Set in pine forests in the south of France is the world's biggest nuclear experiment.
The biggest and most expensive scientific experiment in human history.
This place looks like nothing from the outside, looks like an industrial complex, but inside these buildings, something truly astonishing is happening.
Experts from dozens of nations have joined forces for one very important science experiment. Together, they hope to finally crack a riddle that's remained unsolved for decades, creating virtually limitless amounts of energy through nuclear fusion.
But before I explain what that actually is, it's important to kind of take a step back and grasp why it's such a big deal. If humanity can make nuclear fusion happen at scale, then it could solve one of our greatest challenges, and quite literally change the world.
Thermonuclear burning, fusion if you will, a process that literally is the ultimate source of energy in the universe.
You see, nuclear fusion can generate 4 million times more energy than fossil fuels like coal, oil and gas. It also doesn't emit any harmful greenhouse gases such as CO2, unlike those other forms of energy we just mentioned.
There's no fundamental reason why nuclear fusion is not achievable.
And if that word nuclear makes you feel a little bit uneasy, then fear not, because a nuclear fusion reactor doesn't create any long-lived radioactive waste either. And because there's no plutonium or uranium, using it to make weapons is a lot harder. Instead, it uses tritium and deuterium, both of which are isotopes of hydrogen, and that just happens to be the most abundant element in the entire universe.
So how does all this work, and why are these reactors taking so much longer to master than the ones we've been using for more than half a century? Well, producing energy from nuclear fusion rather than nuclear fission, which is what most traditional reactors do, is a lot more difficult.
Instead of splitting atoms apart, fusion reactors force them together in a controlled way that causes huge amounts of energy to be released. It's essentially what happens inside the sun, when hydrogen nuclei collide at extreme speeds and temperatures to form helium atoms.
Now, amazingly, this machine mimics that process but contains it inside a structure, which, as you can imagine, is not an easy thing to do. All of the construction work you see here at ITER, all the activity going on across this vast site, all those systems, those buildings, all of it revolves around one central enormous device known as the Tokamak.
To put it in very basic terms, just to get us started, it's an enormous chamber that uses giant magnets and a whole lot of heat to create something called plasma inside a vacuum. In just a few moments, I'm going to be journeying to the heart of the Tokamak to learn more about it, and to stand in the very place that in years to come could unlock a new power source that's clean, abundant, and affordable.
That's why it's seen as the holy grail of energy.
Scientists have dreamed of controlling fusion energy, harnessing it to man's needs, freeing him from limited oil supplies, the pollution of coal.
If it sounds complicated, it's because it is. And it's one reason why construction works took decades to even begin. This is the massive assembly hall at ITER, where components come before they're thoroughly checked and then lifted over into the Tokamak. I've been in here before, but walking in here just never gets old. It changes all the time. And it's the most humbling experience. It's massive. Not just physically, but the scale of what they're doing here. This is scientists and construction teams pushing frontiers that have never been broken before. It's such a humbling experience. I got goosebumps just talking about it. It's the best of this industry in one room. It's immense. It's difficult to get across the extreme complexity of this project. Nothing else comes close to it. The Tokamak alone has 1 million components and 10 million individual parts. And it's got to be right. There's no room for error. So all the individual components are brought here first, this massive room, and then these huge cranes on the ceiling, these huge yellow beams above me are cranes that pick those components up and carry them over for assembly in the Tokamak pit. It's extraordinary, it really is.
For instance, with this being one of the biggest and most complex systems of its kind ever constructed, all of the vacuum components have to be 100% leak tight, because you really don't want leaks inside a vacuum, especially when it's part of a fusion reactor. Specialist welding procedures are in place, full-scale leak tests are going to be carried out in the run up to the launch, and amazingly, ITER is even developing technologies that can detect leaks, measuring the width of a hair divided by 1 million. It's easy to see they're taking this extremely seriously. In fact, ITER's beginnings go way back to the 1980s, when Mikhail Gorbachev of the Soviet Union and US President Ronald Reagan formed the International Fusion Initiative. With the Cold War nearing an end, the two leaders wanted to bring forth a new source of energy that is essentially inexhaustible for the benefit of all mankind. After its launch in 1986, other European countries joined the partnership along with Japan, and ITER was officially born. Today, there are 7 ITER members, one of them being Europe with its 27 EU countries. Switzerland and the UK are also partners, but with less direct involvement. Around 45% of construction funding is coming from those European nations, while Japan, China, India, Russia, Korea, and the US are covering about 9% each. It took until 2001 for the design of the reactor to be finalised, along with a cost estimate of €5 billion for the construction. A few years later, a site for the incredibly unique project was selected, and in 2010, building work finally got underway. 4 years were spent building the ground support structure and the seismic foundations for the Tokamak, which itself has been in the works for a decade. The building where it's situated is simply enormous, a 7-storey structure that rises 60 metres above the ground and drops 13 metres below it.
And here it is, all 180 hectares of what's been dubbed the ITER Enclave. It's an enormous chunk of land that's almost the size of Monaco. And it's an area that France gave to the ITER organisation so they could build that incredible machine. And it's crazy to think that in 2010 there wasn't much here. But now look at it. The Tokamak building and assembly hall take up a staggering amount of space, but they're just one part of ITER. Altogether, there are 39 different buildings and technical areas on this huge site.
They include things like cooling towers, a control room, waste management facilities, and a cryogenics plant that'll make the liquid helium needed to cool the 10,000 tons of superconducting magnets. Now, that's important because if they aren't kept close to absolute zero, that's minus 269 degrees Celsius to be exact, the magnetic fields needed to maintain the plasma won't be possible. There'll also be a huge area housing all the high voltage electrical systems,
and two large buildings like this for converting the electricity that comes in from alternating to direct current before it goes over to those massive magnets. What I'm basically standing in here is the world's biggest power adapter.
So, who's responsible for building all this? Unsurprisingly, some of the biggest construction firms in the world are involved, including major international collaborations. One of them is the VFR Consortium, which is delivering 9 of these structures, including the Tokamak complex, the assembly hall, and the control building.
We have been in charge of the construction of the civil works of the Tokamak complex, and we have been installed more than 100,000 embedded plates. We have exhausted work to find cracks and to monitor them and to control. We have faced high densities for river. We have done specific concrete formulas for the Tokamak construction. We have performed complex geometries as well as openings inside the building.
VFR consists of 2 French companies, Vinci and Razelbeck, along with Ferrovial of Spain. Together, they've spent over a decade carrying out civil engineering works on the Tokamak complex.
As you know, this is a very complex project. Many of our people come from Spain, and mainly the people from the other companies were French. So one of the first challenges we faced was this difference of culture. So we've been working with them in a very open and friendly way, and in a very collaborative way, and the outcome of this has been incredible.
To get an even better sense of the insane engineering involved in this massive project, I've been urged to take a look inside its foundations.
Duco, hi.
Fred, hello.
How you doing?
Good, welcome.
Thank you.
Let's go.
Now, crawling underneath a nuclear fusion reactor that weighs as much as 3.5 Eiffel Towers doesn't sound like fun. Thankfully, Duco Janssen, construction manager for the ITER organisation, has agreed to come with me.
This is pretty unique.
This is the basement of ITER.
We're underneath the Tokamak.
You're underneath the Tokamak. So this is the slab which is holding it.
Wow.
You can see around 500 seismic bearings which are supporting it.
So these rubber pads we see, that's isolating the whole Tokamak
absolutely, yeah.
and assembly hall from the rest of the ground. So if there was an earthquake, the energy gets absorbed by those
Yes,
pads.
yes, indeed. And it prevents any shock to the reactor at any point. It's to prevent any issues with the investment, of course, but also during operations to make sure that it's all okay.
When you're down here, the contrast with the assembly hall is really stark because it's so complex and clean up there, whereas down here it's a lot simpler. It feels more like a sort of a standard construction site, but this bit's critically important, right? You've got to have this bit to enable the rest of it to work.
And it's the combination between the very rough civil works combined with the very fine mechanical clean, which is actually also one of the challenges of building it.
It's an extraordinary amount of work for a science project, but what they're trying to do here simply can't be done without going big.
So I guess many people can relate to a housing project, doing up your home, that's complicated enough. But this must just be that times 10, right, on a nuclear fusion reactor. What lengths are you having to go to here that you wouldn't have to go to in a normal construction project?
Yeah, almost everything is unique about this. And a term very much related to ITER is first of a kind. So very many elements that are used here are in 2 ways complicated. It's complicated by
the technology that is used, which is very often novel to create certain curves or certain materials that are unique, but it's also due to the size of ITER. ITER is very large compared to also previous tokamaks, which are already existing around the world. And in order to make these elements in the right dimensions and within the right tolerances, this is an engineering challenge in itself.
Back above ground, one of the key elements during construction of the Tokamak complex was the Ring Fortress. It's a massive steel and concrete bioshield that wraps around the Tokamak. 3 meters thick and 6 stories high, its purpose is to protect workers and the surrounding environment from radiation when the fusion reaction kicks in. As Europe is the host member, most of the buildings and infrastructure are coming from across this continent. But one crucial element was built and supplied by a nation that's much further away. The ITER cryostat is the largest stainless steel vacuum chamber in the world, and it was manufactured in India. Weighing almost 4,000 tons, it surrounds the vacuum vessel and the magnets, ensuring everything stays cool and protected. Its immense size meant it had to be divided up into 54 segments and shipped to Marseille in stages. But that wasn't the end of their journey. They still had to be transported to the actual facility over 100 kilometers away from the sea. Luckily, a specially modified road was built for that exact purpose. Called the ITER itinerary, it's a route stretching all the way to ITER HQ from the nearest port, and it enables the largest pieces of the tokamak, weighing hundreds of tons, to be carried there on the back of huge vehicles.
And I'm currently driving along what is just part of that route. Now, all along here, bridges have been reinforced, junctions have been adapted, roadways have been widened, including just up here where the route passes really close to some pretty big cliffs. Now, it might sound like a lot, but if they hadn't done that, many of the bigger components simply wouldn't have got in.
Other examples of parts that come from outside Europe include the toroidal field coils. Thought to be the most technically challenging element of the entire build, they've now all been successfully manufactured. They're the biggest, most powerful superconducting magnets ever designed, and half of them were produced in Japan. Altogether, these components and their superstructure weigh 6,000 tons, accounting for more than a quarter of the tokamak's overall weight.
The complexity of this project really is mind-boggling, but the amazing team of construction workers who are putting it all together is almost as intricate as the machine itself.
An estimated 15,000 workers from 5,000 companies have taken part in the construction, and around 90 countries are represented in the workforce, making ITER a truly global project. In fact, ITER claims it's the broadest international participation of any science project on record.
It means that teams on the ground here are not just faced with the incredibly complex task of assembly, they're also dealing with different construction methods, different working cultures, even differences in spoken language across the site every day.
For example, although English is listed as the common language across the ITER enclave, only about 15% of the organisation were native speakers in the early part of construction.
The difference of culture, the difference of approaches of how to do things, the complexity of the work, the complexity of the site, lots of people involved in the same site, logistics, and they work differently. They talk different languages. They approach issues in a different way. So this is very challenging and very rewarding also.
One thing that's proven crucial to delivering a project of this magnitude is the use of technology, and we don't just mean things like robots. Digital platforms like Procore have helped boost communication and collaboration, as well as efficiency on a scheme that certainly demands it. Ferrovial's been using Procore to complete a critical contract called TB20. Awarded by Fusion for Energy, ITER's European domestic agency, it involves designing, supplying and installing more than 200 nuclear doors for the Tokamak complex. Since embracing the tech, Ferrovial has seen significant improvements in areas like project management, decision-making and problem-solving.
Testing, manufacturing, construction, and all these records and BIM models require the use of state-of-the-art technologies such as Procore that we couldn't avoid using here. That was a must for us in order to success in the project. Without these kind of tools, we would have been able to carry out these works.
Technological assistance like this has been critical to helping ITER get into its current position, and it's steadily helping it inch towards its goal of coming online in the not too distant future. As of right now, more than 3/4 of all the design, manufacturing, construction, transport, assembly, and installation activities have been completed. So, how on earth is ITER creating what's basically a mini-star here on Earth to generate power? Well, it's time for me to gear up and head to the very spot where it's set to happen.
As soon as you started recording, I've become an absolute idiot at getting dressed.
Here's the entrance to the pit.
Okay, so in here is where the Tokamak's coming together.
Indeed, indeed. A bit like an opera house, in a way.
And this is where we'll be creating nuclear fusion.
That is the plan.
Scientists who wish to control fusion must cope with its enormous heat. They hope to use this technology as a cornerstone for a fusion reactor.
So everything you see on the ITER site, all the infrastructure, the buildings, the assembly rooms, all of it is geared up to this spot.
Yes.
What it's all about.
Yes, it all comes together here.
Yeah.
And everything is more or less supporting the fact that here in the end we'll have the experiment.
And that experiment is planned to go something like this. At the centre of the Tokamak is an enormous vacuum chamber consisting of a large vessel surrounded by powerful superconducting magnets. Hydrogen fuel is released inside, where it forms plasma, a superhot gas full of electrical charge. To reach this point, the hydrogen atoms are heated to extreme temperatures, as high as 150 million degrees Celsius. That's the part where they fuse together and unleash all that energy. These enormous D-shaped magnets, the toroidal field coils we told you about earlier, confine plasma inside the vessel, and there are 18 of them in total. They do this in combination with 6 ring-shaped magnets, the poloidal field coils. Once the plasma has been created and held in position, this place will become both the hottest and coldest place in the known universe.
One very important aspect is the concept of confinement. If you have to keep the heat where it is. And in order to do that, we need very strong magnets. Funny enough, these strong magnets work much better if they are cooled to a very low temperature, only a few degrees above the absolute 0 point. And at the same time, we have a very hot plasma, which is only a few tens of centimeters away from each other.
Yeah, the word mind-blowing gets used a lot, but it really is applicable here, because you're saying this, man, I just cannot believe the scale of the engineering challenge.
Yes, and this is why we have a very international, big team of very smart engineers who are all focusing on the different aspects of it and make sure that it's well thought through.
Once everything is assembled and in place, it'll then be time to turn it on. Now, the original idea was to do that for just milliseconds on low power to create something known as first plasma. But that all changed recently, which we're going to come on to in a bit. Before we move on, it's important to recognise that another team of scientists has already managed to achieve nuclear fusion, but on a limited scale. What ITER are doing is much bigger and takes things quite a step further.
It wants to be the first to create burning plasma. That's where the fusion reaction becomes self-sustaining and continues to generate energy without much additional heating.
Now, the vast majority of the physical infrastructure here is already built and in place, and you can see it all around you, from the main buildings to the support structures, the networking, even the drainage systems. All of that has been constructed. But despite that, and the insane level of scrutiny that goes into making sure that every piece of the puzzle is correct before it gets slotted into place, there have unfortunately been some setbacks.
In November 2022, ITER revealed significant issues which had been identified with some of the components, which left them with no choice but to make time-consuming repairs. There were cracks in cooling pipes and non-conformities in parts of the vacuum vessel.
It means that work on the assembly of the Tokamak is currently paused and can't continue until those problems have been sorted out. It's also not the first time the organisation has faced complications that have caused delays.
Since the initial design was revealed in 2001, there have been rising labour and material costs, advancements in fusion science that had to be factored in, and more time has been spent on assembly and commissioning than first thought. This called for a design review in 2007, followed by another in-depth analysis in 2016. By then, the price tag had reached €22 billion. The target date for first plasma was pushed back to 2025, with full operation expected 10 years later. Then came COVID-19, followed by those technical issues we just mentioned, all of which has pushed things back even further. Another project plan with new dates and costs was put forward in June 2024, and that's currently under review. The idea now is to do away with first plasma altogether and just have the machine start up at full power to enable more advanced experiments, but that won't happen until 2036. The cost has jumped again too, by an estimated €5 billion.
So what stage are we at now? What's the next step? I know there's been some disassembly happening.
Not everything went fluently, and there are some quality aspects that we had to take care of, which were mainly related to the vacuum sectors in itself, so the real confinement vessel, and also with the thermal shields that separate the very warm from the very cold. And both topics were unrelated, but had to be resolved. But fortunately, in the organization, we have made action teams to solve them, and now we are ready to have the first module back into the pit, and that is going to happen early next year.
The project hasn't gone entirely smoothly, but teams here are trying to break a new frontier. They're pushing the boundaries of science, construction and engineering. They're doing something that hasn't been done before, so trying to get it right first time was always going to be a bit of a tough ask. What they're trying to do here could be revolutionary, but the thing is, despite the impressive scale of this place, it's never actually going to produce electricity for the grid. And that's because this place is an experiment. The clue's right there in the title. It's an experimental reactor. The idea is that they use this place to prove that fusion can be done at the scale we need it to be done first, and then for others to come in and learn from what's been achieved here at the ITER site.
But if that sounds like a bit of an anticlimax, then it shouldn't be, because there are multiple other organisations designing and building their own fusion reactors, and they too are making progress.
For physicists here at the Max Planck Institute, these flickering images are a milestone in the hunt for clean, boundless energy.
Germany's brilliantly named Wendelstein 7X Stellarator has already achieved first plasma back in 2015, and since then it's managed to maintain a stable reaction for a whole 8 minutes.
A significant breakthrough in the quest for nuclear fusion energy.
This laboratory first is a first step towards clean energy.
And in December 2022, scientists at the National Ignition Facility in California, part of the Lawrence Livermore National Laboratory, made their own piece of history.
Last week, scientists at the National Ignition Facility achieved fusion ignition.
They became the first to successfully produce more energy through a fusion reaction than was put in to start it. And they did it through a completely different method to ITER's machine. Instead of generating plasma in a tokamak, lasers were fired at a tiny capsule filled with those same hydrogen isotopes used at ITER, tritium and deuterium. The capsule then imploded from the power of the lasers, forcing the atoms to collide or fuse together, releasing energy. From the 2.05 megajoules of laser energy that went in, 3.15 megajoules of fusion energy came out. But that doesn't mean they've solved the whole thing, and that others like ITER might as well give up because they've lost the race. Those lasers take a very long time to fire. That net energy gain is tiny compared to the massive power demands of today, and it's not actually a race at all. Far from it.
All of those organisations, as well as private startups that have begun their own projects in recent years, are all united under one goal: to bring nuclear fusion energy to the grid. Where ITER's a bit different is that it's uniting 35 nations, pulling together all their resources, all their talent, to help this project take a big step and go where no one's gone before.
I think it's a breakthrough in humankind, taking advantage of all this knowledge, this complexity, all these languages, and all these people. It's incredible. It's an incredible opportunity.
It's simply amazing.
Every day there's a new puzzle to solve, and there is new things that pop up that require attention, and the challenge and the fun also is to make sure that in the end, when we go home every evening, we've made a little bit progress further.
Technical complexity, the coordination, all the multicultural participants. There is no other project like ITER.
I've been lucky enough to travel the world and see so many construction projects, and two things really strike me about ITER. The first is how unlike anything else it is. So many other projects are there for transport, they're for housing, they're commercial projects, but this is different. The scale of the ambition, the extent of the engineering, the attention to detail is honestly mind-blowing. It's hard to think that the place where I'm standing could in one day become the birthplace of a new form of energy. This spot could literally see the start of something that could change the world. The second thing that really strikes me is actually just how similar this project is to so many other construction sites around the world. So many construction projects run and are driven by amazing people coming together to coordinate, to plan, to pull off the impossible. And yes, this is more extreme. This takes all that and puts it up in the clouds at an extreme level of ambition. That's the thing about construction. It runs on that same recipe, the same ingredient. Amazing people coming together, making the impossible happen, and shaping our world.
I don't know how motivated and inspired you are watching to this end, but I can assure you that this is a wonderful structure that is mind-boggling. Thank you very much for watching.